A photomask is an opaque plate with holes or transparencies that allow light to shine through in a defined pattern. They are commonly used in photolithography. Overview. Lithographic photomasks are typically transparent fused silica blanks covered with a pattern defined with a chrome metal absorbing film. Photomasks are used at wavelengths of 365 nanometers, 248 nanometers, and 193 nanometers. Photomasks have also been developed for other forms of radiation such as 157 nanometers, 13.5 nanometers, X-ray, electrons, and ions. But these require entirely new materials for the substrate and the pattern film. A set of photomasks, each defining a pattern layer in integrated circuit fabrication, is fed into a photolithography stepper or scanner, and individually selected for exposure. In double patterning techniques, a photomask would correspond to a subset of the layer pattern. In photolithography for the mass production of integrated circuit devices, the more correct term is usually photoreticle or simply reticle. In the case of a photomask, there is a one-to-one correspondence between the mask pattern and the wafer pattern. This was the standard for the 1:1 mask aligners that were succeeded by steppers and scanners with reduction optics. As used in steppers and scanners, the reticle commonly contains only one layer of the chip. The pattern is projected and shrunk by 4 or 5 times onto the wafer surface. To achieve complete wafer coverage, the wafer is repeatedly stepped from position to position under the optical column until full exposure is achieved. Features 150 nanometers or below in size generally require phase shifting to enhance the image quality to acceptable values. This can be achieved in many ways. The two most common methods are to use an attenuated phase-shifting background film on the mask to increase the contrast of small intensity peaks, or to etch the exposed quartz so that the edge between the etched and unetched areas can be used to image nearly zero intensity. In the second case, unwanted edges would need to be trimmed out with another exposure. The former method is attenuated phase-shifting, and is often considered a weak enhancement, requiring special illumination for the most enhancement, while the latter method is known as alternating aperture phase shifting, and is the most popular strong enhancement technique. As leading-edge semiconductor features shrink, photomask features that are for larger must inevitably shrink as well. This could pose challenges since the absorber film will need to become thinner, and hence less opaque. A recent study by IMEC has found that thinner absorbers degrade image contrast and therefore contribute to line edge roughness, using state-of-the-art photolithography tools. One possibility is to eliminate absorbers altogether and use chromeless masks, relying solely on phase shifting for imaging. The emergence of immersion lithography has a strong impact on photomask requirements. The commonly used attenuated phase-shifting mask is more sensitive to the higher incidence angles applied in hyper-NA lithography, due to the longer optical path through the pattern film. Mask error enhancement factor, leading-edge photomasks images of the final chip patterns magnified by 4 times. This magnification factor has been a key benefit in reducing pattern sensitivity to imaging errors. However, as features continue to shrink, 2 trends come into play. The first is that the mask error factor begins to exceed 1, that is, the dimension error on the wafer may be more than 1/4 the dimension error on the mask, and the second is that the mask feature is becoming smaller, and the dimension tolerance is approaching a few nanometers. For example, a 25 nanometers wafer pattern should correspond to a 100 nanometers mask pattern, but the wafer tolerance could be 1.25 nanometers, which translates into 5 nanometers on the photomask. The variation of electron beam scattering and directly writing the photomask pattern can easily well exceed this. Pellicles. The term pellicle is used to mean film, thin film, or membrane. Beginning in the 1960s, thin film stretched on a metal frame, also known as a pellicle, was used as a beam splitter for optical instruments. It has been used in a number of instruments to split a beam of light without causing an optical path shift due to its small film thickness. In 1978, Xie al at IBM patented a process to use a pellicle as a dust cover to protect a photomask or reticle, hence will all be called photomask in the rest of this chapter. In the context of this entry, Pellicle means thin film dust cover to protect a photomask. Particle contamination can be a significant problem in semiconductor manufacturing. A photomask is protected from particles by a pellicle, a thin transparent film stretched over a frame that is glued over one side of the photomask. The pellicle is far enough away from the mask pattern so that moderate to small-sized particles that land on the pellicle will be too far out of focus to print. Although they are designed to keep particles away, pellicles become a part of the imaging system and their optical properties need to be taken into account. Pellicle's material are nitrocellulose and made for various transmission wavelengths. Leading commercial photomask manufacturers, the SPIE Annual Conference, Photomask Technology reports the Semitech Mask Industry Assessment, which includes current industry analysis and the results of their annual photomask manufacturers survey. The following companies are listed in order of their global market share: Advanced Reproductions Corporation, Infinite Graphics Incorporated, Dai Nippon Printing, Toppen Photomasks, Vitronics Incorporated, Hoya Corporation, Taiwan Mask Corporation, Nippon Philcon. Major chip makers such as Intel, Global Foundries, IBM, NEC, TSMC, UMC, Samsung, and Micron Technology, have their own large mask-making facilities or joint ventures with the above-mentioned companies. Worldwide photomask market was estimated as $3.2 billion in 2012 and $3.1 billion in 2013. Almost half of market was from captive mask shops. The costs of creating new mask shop for 180 nanometers processes were estimated in 2005 as $40 million, and for 130 nanometers, more than $100 million. The cost to set up a modern 45 nanometers process mask shop is $200 €500 million, a very high threshold for entering this market. The purchase price of a photomask can range from $1,000 to $100,000 for a single high-end phase shift mask. As many as 30 masks may be required to form a complete mask set. See also, mask work, mask inspection, SMIF interface, nanocanal glass materials. References: Rise v. SYED. 1.3 The Technology History of Masks. Handbook of Photomask Manufacturing Technology. CRC Press. Pages 728. ISBN 9781420028782. Lithography experts back higher magnification in photomasks to ease challenges at times 2000, Sato al., Proc. SPIE, Volume 4889. Pages 50 to 58. M. Yoshizawa al., Proc. SPIE, Volume 5853, pages 243 to 251. C. A. Mack al., Proc. SPIE, Volume 5992, pages 306 to 316. E. Hendrick al., Proc. SPIE 7140, 714007. C.J. Chen al., Proc. SPIE 5256, 673. W.H. Cheng and J. Farnsworth, Proc. SPIE 6607, 660724. Chris A. Mack. Optical Behavior of Pellicles. Microlithography World. Retrieved September 13, 2008. Hughes, Greg. Henry Un. Mask Industry Assessment, 2009 inches. Proceedings of SPIE 7488, 748,803 euro 748,803 euro 13 doi, 10.1117/12.832722. ISSN 0277-786X. Chamness, Lara. Semiconductor Photomask Market, forecast $3.5 billion in 2014. Semi-Industry Research and Statistics. Retrieved September 6, 2014. Tracy, Dan. Deborah Geiger. Semi reports 2013 semiconductor photomask sales of $3.1 billion. Semi. Retrieved September 6, 2014. An analysis of the economics of photomask manufacturing Part A-1, The Economic Environment, Weber, February 9, 2005. Slide 6 The mask shop A-1 registered trademark S perspective, Weber, C.M. Berglund, C.N. Gabella, P. Mask Cost and Profitability in Photomask Manufacturing, An Empirical Analysis. Semiconductor Manufacturing, IEEE Transactions on 19. doi, 10.1109/TSM. 2006.883577. Page 23 Table 1.